Our movie tonight is on balancing chemical reactions. This is something you first learned about in grade 10 science. We're going to continue with that today. Balancing means that we're ensuring that every reacted atom can be found in the products and vice versa, meaning that if you've got an atom that you see in the product, you have to be able to account for it in the reactant side. A balanced reaction will have coefficients, which are numbers, in front of every symbol to show the needed number of each of those materials. Coefficients multiply the number of atoms in an entire compound, but that multiplication will stop when you get to a plus sign or the reaction arrow symbol. Let's do some review. A skeleton equation has no coefficients, so we can see C8H18 plus O2 produces CO2 and H2O. Clearly, this is a good skeleton equation because it's got all the symbols, but if we look at just the hydrogens, we've got 18 on the left and we only have 2 on the right side, so it's not balanced. So SE, skeleton equation, BE, balanced equation. Now we can look at some of these coefficients. If I look at carbon, I have 2 times the subscript 8, which is 16 carbon on the left, and I can see 16 on the right side of the equation, to the right of the reaction arrow, times the 1 understood after the carbon, which is 16 carbon. The hydrogens, 2 times the 18 gives me 36, and again 18 times 2 for the hydrogen on the water side is 36. Oxygen, 50 on the left, 25 times 2. 16 times 2 is 32, plus another 18 is 50. So rapid multiplication skills is important. If you can't do multiplication like that, make sure you have your calculator handy to help you. Moving on now. The ELR chart is something that's going to help us keep track of all those calculations and the numbers of atoms we've got. ELR stands for element left and right to record the number of each type of atom. So if we work on our very first example, what I'm going to do is I'm going to start on the right hand side here. Just going to put the headings E, L, and R. And I'm going to draw them down the page here. And the first reaction has for elements calcium, chlorine, and lithium. That's it. The left-hand side, there is 1 calcium, there are 2 chlorine, and there is 1 lithium. The right-hand side has 1 lithium, 1 chlorine, and 1 calcium. What I find is handy to do is I underline whichever side of the pair is the smaller number if they're not equal. So I underline the 1 for the chlorine because we don't have enough chlorine on the right-hand side. That's a place where I'm going to have to put a coefficient. I have 2 chlorine atoms on the left, but I only have 1 on the right. If I put a coefficient of a 2 in front of the LiCl, because I cannot change any symbols, what's going to happen is the lithium will become 2, and the chlorine will become 2. And all of a sudden the chlorine is great, but now I have a problem with lithium. Lithium, there's only 1 atom on the left, but there's 2 on the right. Good news, there's lithium all by itself on the left-hand side. I put a 2 in front of the Li. Now it's 2. Don't spend time erasing any of these. Cross off and keep going, even though you should be using a pencil to do this. That way we can go back and have a sense of how we got where we got to. So we have 1 calcium on the left and right, 2 chlorine on the left and right, 2 lithium on the left and right. It is now balanced, which means any place I have a gap, I go back and fill in with 1s. You must go back and fill in with 1s. One last thing when you're balancing, if you can find that you can divide all those coefficients by some number, you need to simplify the ratio. Let's look at another example. Here we have sodium bicarbonate decomposing to produce sodium oxide, water, and carbon dioxide. We're going to again do our count. So we have sodium, hydrogen, carbon, and oxygen. Originally we have on the left-hand side 1, sodium, 1 hydrogen, 1 carbon because 1s are understood, and we have 3 oxygen. On the right-hand side, we have 2 sodium because of that subscript of 2. We have 2 hydrogens because of the subscript on the hydrogen. We have 1 carbon, so it looks like carbon is nicely balanced. Oxygen, we have to be really careful because there's 1 in the Na2O, 1 in the H2O, and 2 in the CO2 for a total of 4. So now when I go to underline, wow, look at that. I'm short sodium, hydrogen, and oxygen all on the left-hand side, so I'm going to have to do something with the left-hand side. Not quite sure what to do with that oxygen yet because it's spread out in multiple compounds. Let's deal with the other elements first. I can fix sodium by putting a 2 in front of the NaHCO3. And what that's going to do is it's going to double everything on the left because there's only one reactant. So it's 2, 2, 2, and 6. And so now the sodium's good, the hydrogen's good, carbon's low, and oxygen's low. Again, oxygen is all over the place. 3 different compounds, so let's hope it works out. Let's deal with that carbon first. There's 2 carbon on the left, but only 1 on the right. By multiplying this CO2 by 2, 2 times the 1 understood is 2 carbon. So now the carbon is 2. Oxygen we have to recount. So there's 1 in the Na2O, 1 in the H2O, and 2 times 2, which is 4 in the 2 CO2s. So 4 plus 1 plus 1 is 6. This is all nicely balanced. We go back and fill in with 1s. Moving on to the last slide now. I'm going to put up the 2 examples, and I'm going to put the charts down below because these run a little further off to the side. So again, I'm going to do my count with my E, L, and R. I'm going to do example 3 first. This time around I've got copper, sulfur, and aluminum. On the left side I have 2, 1, and 1. The right hand side I have 2 aluminum, 3 sulfur, and 1 copper. So this one's a mess. I've got not enough copper on the right, not enough sulfur or aluminum on the left. Let's leave the individual atoms, the aluminum all by itself, the copper all by itself, till last. Deal with the compounds. Usually if we start with the messier looking symbols, the more complicated symbols, that's the best place. So because the copper metal on the right is all by itself, I'm going to look at the left-hand side. I need more sulfur, I need more aluminum. I'm going to deal with the sulfur first. I have 1 on the left, I need 3. If I put a 3 in front of the Cu2S, good news, sulfur goes to 3, but copper goes to 6. Good thing I didn't fix it already. So sulfur is now good. I'm going to deal with the aluminum on the left as well. If I put a 2 in front of the Al, that means the left-hand side now has 2, so the aluminum and the sulfur are now balanced. All I have to do is deal with the copper. So there are 6 coppers on the left, but only 1 on the right. 6 in front here, 6 times the 1 understood is 6, so now I have 6 copper, and this is all balanced. There's a gap right here in front of the Al2S3, fill in with a 1. Last example, number 4. We've got an ELR. Notice how a little bit of space for the L and R helps out because you might have to go back and redo a few things. So this time around we've got a double displacement, we've got aluminum, we've got nitrogen, we've got oxygen, we've got iron, and we've got bromine. This is going to get a little messy. The aluminum, there's 1 nitrogen, 1 understood after it times the 3 outside the bracket is 3. Oxygen is the 3 inside the bracket times outside the bracket, which is 9. Iron is easy, it's 1, and the subscript after the bromine is 2, so that worked out really nice. Right-hand side, I see 1 iron, the nitrate, the 1 inside the bracket times the 2 outside gives me 2 nitrogen. 3 times the 2 gives me 6 oxygen. I've got 1 aluminum and 3 bromine. Wow, I've got aluminum good, iron good, but the bromine and the oxygen and the nitrogen are not good. Something to look for, if I look at the bromine, I've got a 2 and a 3 ratio, and notice that they're each in 1 compound apiece. 1 compound on the left, 1 compound on the right. Ultimately, I'm going to need 6. Sometimes you use the phrasing lowest common denominator from your fractions. If I see that a substance is only in 1 compound on the left and is only in 1 compound on the right, it's got to be a direct relationship between the two. And so one of the things I can do is I can say, well, if I put a 3 in front of the FeBr2 and a 2 in front of the AlBr3, what that's going to do is it's going to give me 6 bromine on both sides. That was easier than I was hoping. Let's see what happens. Now the iron on the left is now 3, and the aluminum on the right is now 2. All right, let's follow those, see if those nitrogen and oxygen work themselves out. That means that on the left-hand side, I've got to have more aluminum. So if I put a 2 in front of the aluminum nitrate, that means on the left-hand side, I'll have 2 aluminum. Now we got to be careful with our multiplication. Nitrogen has a 1 understood times the 3 outside the bracket, which is 3, times the 2 out front, which is 6. Oxygen will be 3 times 3, which is 9, times the 2 out front, which is 18. Wow, numbers are getting big. But let's focus on that iron because that was easier. I got 3 iron on the left, but only 1 on the right. So if I put a 3 in front of the iron 2 nitrate. Now the iron is 3. Nitrogen is 1 understood times the 2 times the 3, which is 6. And the oxygen is 3 times 2, which is 6, times 3, which is 18. And it worked out beautifully. I could have used the subscripts on the nitrates as well to get there. Thanks for watching.